Colliding neutron stars are among the most violent and fascinating events in the universe. These cosmic collisions occur when two neutron stars, remnants of massive stars that have exhausted their nuclear fuel and undergone supernova explosions, spiral toward each other due to gravitational wave emission. The dance of these incredibly dense objects is a process that unfolds over millions of years, culminating in a cataclysmic merger that releases an enormous amount of energy. As the stars draw closer, they accelerate, producing increasingly intense gravitational waves that ripple through the fabric of space-time. These waves carry information about the stars' masses, orbits, and the extreme conditions in their final moments. The detection of such waves provides unique insights into the fundamental laws of physics. The moment of collision is marked by extreme conditions of density and temperature, creating an environment ripe for exotic physics. The neutron stars merge to form a single, incredibly massive object, which may collapse into a black hole almost instantaneously or remain as a hypermassive neutron star for a brief period. This process ejects a substantial amount of neutron-rich material into space, which undergoes rapid neutron capture, or R process, nucleosynthesis. This phenomenon is responsible for creating many of the heavy elements in the universe, such as gold, platinum, and uranium. The light emitted from this material, known as a kilonova, provides a unique observational signature that allows astronomers to study the origins of these elements. The electromagnetic signals accompanying these collisions are equally spectacular. High-energy gamma-ray bursts, some of the most powerful explosions in the universe, can be triggered by neutron-star mergers. These bursts emit focused beams of gamma rays, which, when aligned with Earth, can be detected by space telescopes. Following the gamma-ray burst, other wavelengths of light, ranging from X-rays to radio waves, can reveal additional details about the event. These multi-messenger signals, combining gravitational waves and electromagnetic observations, offer a comprehensive view of the collision, allowing scientists to probe the nature of dense matter and test theories about the behavior of matter under extreme conditions. The scientific implications of studying colliding neutron stars extend far beyond the events themselves. These collisions serve as natural laboratories for testing general relativity, as they involve gravitational fields far stronger than anything that can be created on Earth. They also provide constraints on the equation of state for neutron star matter, which describes how matter behaves at incredibly high densities. Understanding these properties has implications for fundamental physics, including the search for a unified theory that combines general relativity with quantum mechanics. Furthermore, the observation of kilonovae and their aftermath sheds light on the chemical evolution of galaxies and the cosmic abundance of heavy elements. The discovery of colliding neutron stars and their observation using both gravitational wave detectors and traditional telescopes represent a revolution in astrophysics. The first such event detected in 2017, known as GW170817, confirmed many theoretical predictions while raising new questions. It demonstrated the power of collaborative efforts between astronomers, physicists, and engineers, as hundreds of observatories worldwide worked together to study the event. This collaborative spirit continues to drive progress in the field, with advancements in technology and theory promising even more profound insights into the nature of the universe and the fundamental forces that govern it.